talk of the morning session with Rongfeng Sun, who will talk about an invariance principle for a random walk among a Poisson field of moving traps.
Yeah. Thank you for the introduction, and thanks for the invitation. So I'll talk about joint work with Shiva Shraya and Alex Drevitz. Okay, so basically what the model we consider is a random walk which is trying to survive among a field of traps. So the random walk is denoted by x here. So let's take for simplicity x to be a simple symmetric random walk on the d-dimensional integer ladders. And the traps are represented by a potential. So this you think of it as a space-time field. So at the time t at position x, you have a random variable which is non-negative, and so that is called the trapping potential. So whenever a random walk comes to a position x at time t, then it is being killed at an exponential rate, where the rate is simply some parameter gamma multiplied by the potential that you see. So in particular, if a gamma is equal to infinity, which is also allowed, it means that the moment you come to a location where psi is strictly positive, then the random walk is killed immediately. So that's what the infinite killing rate means. So we are interested in the case where the potential will be generated by Poisson random walks, the occupation field of Poisson random walks. So that's what the title suggests. So formally, you can think of also the trapping potential as a random environment or disorder. So if I fix a realization of the trapping potential psi for all space-time, then you can try to compute what is the probability that the random walk will survive up to time t. Now, because there is exponential rate of killing, so therefore the survival probability is simply the exponential of the total killing rate that you see along the random walk path. So this is a functional, so if you take expectation with respect to the random walk, then this is the so-called quench the survival probability of a random walk in this realization of the space-time trapping potential. You can also take expectation with respect to the randomness, the environment. Then this defines the so-called annealed survival probability. So the basic question that we are always interested in are the following. The first question is, what can you say about the rate of decay of the survival probability? So you can ask this question for the quench case, and you can also ask the same question for the annealed case. Then the second question is that now condition on survival up to time t, either in the quench setting or in the annealed setting, what can you say about the behavior of the random walk? Is it super diffusive, is it subdiffusive, or does it behave in certain ways that is different from what you expect for normal random walk? So these are the basic questions that we're interested in. And so the trapping problems, they have an origin from the basically chemical reactions literature. So this is called reaction kinetics. So basically it means that this is a subject where people study different species, different type of molecules interacting with each other. Each type of molecule can undergo diffusion. And so that's the origin of this kind of problem. And also transport processes where a particle is being transported through diffusion in a random medium. So Frank den Hollander and Weiss had a survey article a long time ago. And it is also intimately connected to Schrodinger with random potential. So the trapping potential, you can think of it as the random potential in the Schrodinger operator, and then the motion of the random walk generates a Laplacian operator. Okay, so classically, what people have studied is the case when the trapping potential does not change with time. So they are static. So imagine that initially at each lattice point, you put on a Bernoulli random variable. If the Bernoulli random variable is 1, then you put a trap there, and otherwise there is no trap. So that's a very classic problem that is studied by Donsker and Varda. And the case we are interested in is the case when the traps actually themselves undergo independent motion. So if I initially put some random walks, ID number of random walks at each lattice point, and I let them evolve as independent random walks, then as time goes to infinity, they will stabilize to equilibrium field, where the number of particles at each lattice point is ID Poisson distributed. So that's what the title suggests. We consider a stationary field of Poisson traps, where the marginal distribution at each time are just the ID Poisson random variable. So this is in contrast to the static case, where the traps do not move. Okay, so for the case when the traps are static and do not move, this has been studied extensively in the probability literature. So in the continuum, you can imagine that what you should do is to draw a boson point process, and then around each boson point you place a ball. So that will be your traps or obstacles. So this is a classic subject that is related to the Brownian motion among bosonic obstacles. And if you try to compute a new survival probability, this is related to the volume of the Wiener sausage studied by Donsker and Varda. So the bosonic obstacle, there is a classic book by Alan Stitman using the method of enlargement of obstacles. And there are also many other results on this topic. The reason that this can be studied fairly well is because there are a lot of techniques like spectral methods, and when the potential does not change with time, you have more techniques. But when the traps are dynamic, changing with time, then most of these techniques do not work anymore. So there are many fewer results. There's also a connection between the trapping problem and the so-called parabolic Anderson model, namely that if I look at the survival probability as a function in space and time of where the random walk starts satisfies PDE. And so that is basically this parabolic equation where you have the random walk generator here, and then you have the trapping potential that you see with a minus sign gamma, which means that a solution is being killed at exponential rate. So that is killing rate. There's a time reversal because in the Feynman-Katz representation of the solution of the heat equation, there is always a time reversal. The Brownian motion has to evolve backwards in time. So that is why there is a time reversal here. So therefore, if you consider the survival probability as a function of the starting point in space and time, then it's connected to this parabolic Anderson model. So that's a separate topic of study by itself, and there's extensive literature as well. So in particular, there is a book by Wolfgang Koenig on the parabolic Anderson model. For the case when potential depends on space and time, it evolves with time, there is one class of potentials which have been studied extensively by Frank de Hollander, Jürgen Gartner, and Greg Maillard, Dirk Erhard, and the co-authors. So that is when they consider the trapping potential to be generated by some interacting particle systems on the integer lattice. So this could be exclusion process, where the potential will be 1 if there's a particle at the lattice point at that time, or 0 otherwise. Or it could be independent random walks, as we consider here. And it could be other interacting Avogadro model, etc. So this is one type of space-time potential that have been considered quite a lot. And in particular, Frank and Jürgen and Gregory Maillard, they consider the case where you take psi to be the field of independent random walks, but they consider positive potential instead of negative potential. So if the potential is positive, then you should interpret it as random walks are branching. It branches at a certain rate given by this gamma times psi. Well, here we consider killing. Okay, so formally, if you want to define the solution, if you want to define the occupation field, then you can just write it as a counting random variable. You count all the random walks starting at time 0 from position y, and then you count all of them, and you see that how many of them are sitting at position x at time t. So that's just a more precise way of writing down what is the occupation field of these independent random walks. And so the results we have so far on the survival probability are the following. So we consider the annealed survival probability, which is easier to analyze, which is also in some sense more interesting because you don't always have exponential decay. The quench survival probability, you can show that it always decays exponentially in time, or more surely, but we don't have explicit characterization of the rate of decay. While for the annealed survival probability, we can compute the rate of decay. In fact, in dimension 1 and 2, it will have a sub-exponential decay, and we can compute the rate precisely. So in dimension 1, it is known that the survival probability decays like e to the power of minus constant times square root of t. And the constant is square root of 8 over pi. In dimension 2, the rate of decay of the annealed survival probability is t over log t, and the constant is pi. In dimension 3 and higher, we don't have a formula. We just know that the rate exists. And so what is interesting to observe is that in dimensions 1 and 2, the rates here actually do not depend on gamma. Remember, gamma is the rate of killing. So you have the occupation field, and then this is multiplied by gamma. So gamma, in some sense, measures the strength of interaction between the random walk and the environment. Now, in dimension 1 and 2, you see that the exponential rate of decay for the survival probability does not depend on this strength of interaction. So this is already sort of heuristically suggestive that condition on survival, the random walk probably does not meet any trap at all. That's why the interaction strengths with the trap do not appear in the formulas. While in dimension 3 and higher, there should be dependence on gamma. Okay, so just a word about how you come to these bounds, especially in dimension 1 and 2. How do you come to this lower bound, say, let's say the lower bound of these survival probabilities? Well, the strategy is exactly the same as in the case when the traps do not evolve in time. So that's the classic case studied in the literature. So the strategy for the lower bound is you simply create a ball where the radius depends on time. So time is t, then radius is rt. And what you do is that you force the initial condition so that there is no traps inside the ball at the time 0. And then the random walk, then you also impose a condition that from outside, the traps will never enter into the ball. So in the static case, if the traps do not change with time, then this is done at time 0. You do it at time 0 once and for all. You insist that there are no traps inside the ball. And then you insist the random walk to stay inside the ball up to time t. Well, in a dynamic case, this is more costly because you also want the traps not to enter the ball at all. So this is even more costly. But if you follow this strategy, then you can compute the lower bound on the survival probability, which is correct in dimensions 1 and 2. And so in dimension 1, the optimal radius of the ball you want to clear is t to the power 1/3. In dimension 2, the optimal radius of the ball you want to clear is log of t. In dimension 3, if you do the calculation, you find that the optimal radius of the ball you want to clear is order 1. So in dimension 1, the cost, this optimal radius is exactly the same as in the case when the traps do not change with time. But in dimension 2, the radius is much, much smaller. And in dimension higher, it is order 1. So as I mentioned, when the traps do not move in time, then Donska and Vardan showed that the survival probability has exponential decay with a rate that is given by t to the power d over d plus 2. So when d equal to 1, this is exactly 1/3. But in high dimensions, you still have a polynomial exponent. Okay, so this is the lower bound, which essentially captures the correct behavior in dimension 1 and 2. And in dimension 3, it is probably correct as well, but you don't know what is the precise prefactor in front of RT. So that probably cannot be captured by this lower bound strategy. But if you follow this strategy, then it gives you some suggestion on what the behavior of the random walk should be under annealed survival. For example, in the immobile case, when the traps do not evolve in time, people have analyzed the behavior of the random walk conditioned on annealed survival. Basically, what happened is that this ball, it has a random center. There's a random center of the ball that you can identify explicitly. And then the random walk basically behaves asymptotically like a random walk or Brownian motion conditioned to stay inside this ball. So this is called the taboo process. So if I follow the same strategy, if the lower bound for the mobile trap case is also correct, then you would expect that in dimension 1, the random walk would basically be localized. Of course, there's a question of whether the lower bound is correct or not, but you expect the random walk to be localized in dimension 1. In dimension 2, you expect it to be localized even further, maybe on the logarithmic scale instead of polynomial scale. And in dimension 3 and higher, this is where things should be different. The lower bound strategy suggests that it should be localized in the ball of radius of order 1. But if you think about it more carefully, it doesn't quite make sense, because the time it takes to create a clearing of size of order 1, this will only take order 1 time. It doesn't take very long to create sort of open space around the random walk so that you don't see traps. But once you have created such a clearing, then you would expect that there will still be fluctuations over time. So therefore, the clearing should be drifting around. And so therefore, this suggests that in dimension 3 and higher, if I condition random walk survival, then it is probably going to be diffusive. And so that's basically the main result we want to prove, that in dimensions 6 and higher, I will explain the reason why 6 and higher, therefore, we can show that indeed conditional survival, the random walk actually satisfy the invariance principle. So that's the main result I want to present. So I'm getting ahead of myself. So let me first try to recall some early results we have done for dimension 1. So in dimension 1, let me first reformulate the annealed survival probability in the following way. So annealed survival probability means that you have to integrate out randomness in the random walk. You have to integrate out randomness in the potential, in the trapping potential. So you can always interchange the two expectations. So let me first integrate out the randomness in the trapping potential, which is the Poisson field. So it turned out that this expectation is something that is quite nice. Thanks to the Poisson structure, we can write down a much simpler formula for the survival probability of the random walk for given realization of the random walk trajectory. So let me denote this inner survival probability by Zx gamma t to emphasize that this is for given realization of the random walk path. So this is just a denominator, so that's a normalizing constant or just the annealed survival probability itself. And so in the paper some years ago, we showed that in dimension 1, the random walk conditional annealed survival actually is subdiffusive. So we have a bound on lower bound, the upper bound on the supreme norm up to time t, but they don't match. So lower bound is t to the power 1/3. So that's exactly the exponent that appears in the lower bound strategy. You create a ball of clearing of radius t to the power 1/3. But the upper bound, we believe that it is not optimal. So we get a bound of t to the power 11/24. So that is just slightly below 1/2. And but nevertheless, this shows that the random walk is subdiffusive. So open question is, can we identify explicitly what is the correct exponent for the fluctuation of the random walk? And then if you can do that, can you prove some convergence result, whether it converges to Brownian motion condition to stay inside the ball or not? So this is still open. And let me mention that Mehmet also proved the improvement of this upper bound for the continuum case. When you have Brownian motion among Poissonian obstacles, they improved the bound from 11/24 to 5/11. But still it's quite far from 1/3. So that is the open question in dimension 1. And in dimension 2, also there's no results. There's no results so far on subdiffusivity either. And of course, we have no results on the quenched case. So now let me come to the main result I want to present, which is to consider dimensions high enough. So here the result is for dimension 6 and higher. And we prove that there is convergence to a Brownian motion where the diffusion constant sigma d depends on dimension, depends on random walk. It is finite, but for the moment we only show that it is strictly positive when the interaction strength, when the killing rate gamma is sufficiently small. The reason is because the diffusion constant can be written as an infinite series, namely it's the sum of basically the time-time covariance, time-time correlation. And if you look at the formula, it's hard to read whether this infinite sum is equal to 0 or not equal to 0. It's only when the gamma is sufficiently small, then the first term in this infinite sum, infinite series is already clearly the dominant one. And then we can conclude that diffusion constant is positive. So I don't know if there is general techniques which allows you to show that when you sum of the time-time covariance, it must be non-zero under certain reasonable assumptions. So for the moment, we only can show this for gamma small enough. Okay, so this remark I already explained, namely that on one hand, you expect the low bound strategies suggest that random walk is localized in ball of radius 1. But if you think about it carefully, this shouldn't be the case because the ball is going to drift around. And so that is consistent with what we proved. Okay, so the question is, do these results hold in dimensions 3 and higher, not just dimension 6 and higher? And can we show that the diffusion constant is strictly positive for all gamma? Because otherwise, if it is not strictly positive for all positive gamma, then this means that there is some sort of phase transition that we haven't understood. And we don't believe that that is the case, but still something to work out. Okay, so the way we prove this result actually is not by standard probabilistic techniques. We use something that is called thermodynamic formalism, which is a topic from dynamical systems and ergodic theory. So I'll try to explain that how we recast the problem in this thermodynamic formalism framework, and what is the thermodynamic formalism about. So the starting point of analysis is basically to rewrite the survival probability for a given realization of the random walk. So as I mentioned that given realization of the random walk, the survival probability is computed by integrating out the Poisson field. And thanks to the special structure of the Poisson field, it turns out that you can rewrite this as the exponential of a single time integral. So let me explain that what is this time integral here. So suppose that this is my random walk trajectory x, this is t. And what is written as the Vx as x here means the following. So I take a time s in between from 0 to t. What I do is that I run a random walk y backwards in time. So this is my random walk y. And I look at basically the Laplace transform of the collision local time between the forward trajectory of x and the backward trajectory of y. So you simply compute the Laplace transform. That's what this expectation is. You compute the Laplace transform of the collision local time between y and x in this way. And so that defines the Vx as x. And then you do it at each point along the random walk trajectory x. You do it along each point. You integrate over time. And that gives a different representation for the survival probability of the realization of the random walk trajectory x. So this is a very special formula that only works when you have a Poisson field. But this is the starting point of analysis. So the way we are going to rewrite it is basically to discretize the time. And so we, in particular, let's assume that t is an integer. And I'm going to cut the time integral into pieces of length 1. So I discretize time. And then I'm going to represent everything in terms of the increments of the random walk. I think of the increments of the random walk on each unit time interval as a basic input, and then I'm going to rewrite everything in terms of increments of the random walks. But before I do that, first let me try to make a simplification or make a modification that fits the thermodynamic formalism better. And what I do is that I extend the random walk x backwards in time by infinite trajectory, which for simplicity you can assume to be constant 0. So I extend it backwards all the way to time equal to minus infinity, so that you get a picture that is more translation invariant, and you don't have this finite path memory issue. So that's what I do. And so that's what this integral from 0 to infinity is about, because before you only integrate the starting point of the random walk y on this interval, but now you can extend all the way back to back to minus infinity. And so let's modify the law of the random walk conditional survival accordingly as well. So before this was the weight corresponding to the trajectory x. Now let me replace this weight by this modified weight. We have added extra history to the random walk x. Okay, so the claim is that in dimension 5 and higher, this modification has a negligible effect on the law of the random walk conditional and neo survival. So that's one thing that one can check later. I'll explain that why the result is for dimension 6 and higher, not the 5 and higher, even though here you only need the dimension 5 and higher. Okay, so now to prepare for the formulation in terms of thermodynamic formalism, the first observation is that if I look at these Laplace transforms of the collision local times, they only depend on the random walk increments backwards in time. Right? They do not depend on the position of the random walk at time t. They only depend on the increments of the random walk. So therefore, I can rewrite everything in terms of increments of the random walk x. So let's introduce the symbols for the increments of the random walk. So let's take the time interval n to n plus 1 of the random walk trajectory, and let's consider the increments of the random walk on that time interval. So this means that I center it from the starting point at time n. I look at the displacement on this time interval. So this removes the translation variance. And next, we can rewrite the weight that we introduced before. So remember that this weight, which is essentially the weight for the survival of the random walk. So let me rewrite this weight by discretizing time. So instead of writing as an integral from time 0 to time t, let me write it as a summation of the different time intervals. So there are t intervals of unit length. So let me write it as a summation from 1 to t. And on each interval, what we have is basically the following. So you have time n to n plus 1. So on this interval, what we have is basically the integral of this point s. And for each s, you have the Laplace transform. And so that's this integral here. So the integral restricted to the interval n minus 1 to n that's written here. And what is inside is simply a Laplace transform for this random walk y starting from s. But nevertheless, everything here is a function of the increments of the random walk x. So therefore, I can write everything as a function phi on the increments of the random walk up to the terminal time n. So if you are looking at the contribution on the interval n to n plus 1, then everything depends on the increments of the random walk from n to n plus 1, n minus 1 to n, n minus 2 to n minus 1, etc., etc. So all these are past it's a function of the past increments up to the time you are interested in. The complication is that it depends on the entire history. It does not depend on the behavior of the random walk locally. It depends on the entire past. And that is the complication, but that is also the defining feature of this thermodynamic formalism framework. Okay, so once we have written all this down, then we are almost ready to apply the thermodynamic formalism. So first, let's try to think about the problem in terms of increments. So before I think about the behavior of the random walk trajectory, if you quotient out the translation space, namely if you disregard the endpoint, shift the endpoint back to 0, then the random walk trajectory is in one-to-one correspondence between the increment with the increments of the random walk. So therefore, instead of thinking of a probability measure on the trajectory, let's think in terms of the probability measure on the increments of the random walk. Then this weight here, the weight that is written down here can be regarded as not a weight on the random walk trajectory, but as a weight on the increments. So this I denote by z eta gamma t. So this is simply a weight on the increments that you see. So eta I represents the increments on the time interval I minus 1 to I. And when I is less than 0, we assume by assumption that the increments are identically equal to 0. So if I write it this way, then this allows us to apply thermodynamic formalism, which is also called the Markov shifts of type S. S refers to the space where the increments, where the symbols are living. And also it's sometimes called the symbolic dynamics. So now let me explain what the thermodynamic formalism is about. So the basic idea of thermodynamic formalism is the following. So we have rewritten everything in terms of the symbols, eta 1, eta 2, etc., etc., which in our case corresponds to the increments of the random walk. And in general, what you have is the same, namely that you have a space of alphabets. So let's write it as eta minus k minus plus 1, eta minus k plus 2. eta minus 1. So this is the space which we are interested in. And so each of the etas, they are elements of the alphabet space. So this is called the alphabet space. So normally in the theory of thermodynamic formalism, the alphabet space is finite, equipped with a counting measure, or it's countable with a counting measure, and sometimes it can also be compact. But the most common case is when it's a finite or countable with a counting measure. Now in our case, the alphabet space will be the space of Cadillac random walk trajectories, because we want to take the increment of the random walk on the unit interval as a symbol. And so this generates a space that is not finite or countable, and also it's not compact. So that's the main complication in our application of thermodynamic formalism. And then we're interested in these one-sided semi-infinite sequence spaces, which is the sequences that I write down. So in some sense, you can think of it, the theory of thermodynamic formalism, as some sort of Markov process on this state space, on the state space sigma, where the evolution is that every time you evolve by one step, you simply attach a new symbol to the right-hand side. And so this generates another element of this semi-infinite sequence space. But the fact that the evolution depends on in the entire history is different from our usual Markov chain. Usual Markov chain, you just depend on the current location, the current symbol, or maybe a finite memory Markov chain depends on the finitely many symbols in the past. But here, the evolution depends on the entire history, so it depends on all the symbols from the present time to the infinite past. So that's the complication. And to govern the evolution on this sequence space, you need a potential. So that is denoted by phi. So phi is the potential on these semi-infinite sequences. And once you have all these ingredients, then we are ready to define an operator that is similar to the Markov operator, except that here it is not going to be conservative, because you think of phi as a potential. So when you jump to a new location, the trajectory, the probability is replaced by a basically exponential weight. So exponential weight is determined by the potential. So it will not be a Markovian operator, but rather you should think of it as like a Gibbs measure. The Gibbs measure changes the measure of the reference random walk or a process by exponential weight. And so this is similar here. So this operator is called the real transfer operator. In the literature, it is normally denoted by L sub phi, but here let me write it as pi, because of analogy with the Markov operator of a transition matrix pi. So the operator does the following. So you start from an initial state eta in this semi-infinite sequence space, and then you evolve it by attaching to it a new symbol, sigma, zeta. So you attach a new symbol, zeta. So that's the evolution. But then you are going to, so zeta is going to be sampled according to the reference measure. So we assume that the alpha space is equipped with the reference measure mu. In our case, mu will just be the probability measure of the random walk trajectory on the unit time interval. And then you are going to change the measure by this exponential weight given by the potential. So the potential is simply phi acting on this new symbol, acting on this new sequence, eta appended by the zeta symbol. So then you take expectation against the test function phi. So this is really the analog of the Markov operator for Markov chain, except that you have exponential weight instead of a transition probability kernel. But this is pretty standard in the framework of Gibbs measures. So that is why it's called thermodynamic formalism, because the language is really in the language of statistical equilibrium statistical physics. Even though you are doing symbolic dynamics, working with basically the sequence of symbols, but still the formulation is basically in terms of Gibbs measures and things like that. Okay, so that's the operator acting on test functions. But of course, there's also the adjoint operator, which acts on measures. It's not going to send probability measures to probability measures, but it will send the finite measures to finite measures. So that's the adjoint. So the kernel of the adjoint is similar. If I start from an initial state eta in this infinite sequence space, then the kernel is simply given by this exponential weight multiplied by the reference measure on the single symbol that you attach. And you can also apply this adjoint operator on any initial finite measure. And this is well defined. Now, if I apply the operator multiple times, just like the evolution of a Markov chain on the initial state, on the initial distribution, you can write down what is the measure after n steps of iteration. So if you write it out, then you have the initial state that is sampled according to the reference initial measure nu 0. But then if you look at the total aggregate effect of these transitions, the aggregate effect is simply this exponential factor multiplied by the reference measures of each new symbol that you attach. Every time you evolve by one step, you attach a new symbol sampled according to the reference measure. But then you have an exponential weight, so you have to add up, you have to multiply all the exponential weights together, which gives you this additive factor. So the meaning of this additive factor is that every time you evolve by one step, then you look at the entire history, you apply the function phi or potential phi, and you add it to the exponent. And so the whole thing is basically the density with respect to the reference measure. So the reference measure is simply nu 0, the initial condition, multiplied by the product measure of the symbols you sample for n steps, and then this exponential the Gibbs weight. So a priori, this measure is not going to be a probability measure. Nu 0 pi n is not going to be a probability measure, but of course you can always normalize it to be a probability measure. If I normalize it to be a probability measure, then we see that this is nothing but what we call Gibbs measure. Right? Gibbs measure means that you have an underlying process. In this case, the underlying process is has this reference measure, and then you weigh it by some exponential weights, and so that's this exponential scale, and then you normalize everything to be a probability measure. Okay, now at this point we can go back to the formulation that we have written. So the formulation we have written is exactly in this form. Remember that if I take the random walk increments up to time n, up to time t, say, then we saw that if I look at the probability measure on the increments that we have, it is exactly of this form. So the Gibbs weight is simply given by the exponential of the sum of times from, say, 1 to the terminal time t. And for each time interval, that we basically have this potential phi. And the phi depends on the entire history of the random walk. So that's why phi depends on the increments from time minus infinity to time n. So it depends on all these past symbols. And the measure we are interested in for the increments is exactly the Gibbs measure associated with that exponential weight. So what will be the analog of nu 0 here? Well, the analog of nu 0 in null setting, by assumption, is simply the 0 increments. Because we assume that random walk starts with constant initial condition, constant position 0 from time minus infinity to time 0. So the E dash will be identically equal to 0 for I less than or equal to minus 1. And for E dash between 1 and t, we basically sample them according to independent random walk increments on unit time intervals. But then there is these exponential weights coming from the potential that allows you to define the measure we are interested in. So therefore, what we have written here is exactly in the same framework of this thermodynamic formalism. The only problem is that the symbol space, the alphabet space, is complicated. Because traditionally, people consider finite or countable alphabet space. But here, our alphabet space is non-compact because it's a space of Cadillac trajectories on the unit time interval. Okay, so to deduce the result that we want to prove, namely the invariance principle, what we need are two results, or we need to extend the two results from the theory of thermodynamic formalism. The first result is a Perron-Frobenius theorem, which is a theorem about the operator pi, the transfer operator. So for Markov chains on the finite space, we know that there is basically, if I look at the transition matrix, let's assume for simplicity that the transition matrix the entries are all strictly positive. Then we know that there's a dominant eigenvalue that is simple, and there's also a uniquely associated eigenmeasure, which is the invariant probability measure. So that is a Perron-Frobenius theorem, and you have infinite dimensional analog of this as well. So here we basically want something similar. Here the operator pi acts on in an infinite dimensional space, the space of infinite sequences, semi-infinite sequences. So it's not compact, it's very complicated, but still we would like to have a Perron-Frobenius theorem which tells us that there is a simple dominant eigenvalue, which is strictly positive, and then there is also a uniquely associated eigenfunction that is positive everywhere, and associated eigenmeasure that is also positive everywhere. So that is the first thing we want. And once we have a Perron-Frobenius theorem, then what we can do is that we can perform an H transform of the operator pi to generate the transition kernel of actual Markov process. Here, this is not a Markov because the weights are not preserved. But once you have a performability theorem, then you can transform everything into a Markov process. So once you have a Markov process with a stationary distribution, which is unique, then what we would like to do is basically to have a mixing for that stationary process. Because once you have stationary for the mixing process, then there are standard invariance principles and central limit theorems for mixing sequences. You just need to verify that the conditions of the Martingale COT is satisfied. And that is where dimension larger than or equal to 6 comes in. Because in order to satisfy the mixing, we need dimension to be at least strictly larger than 5, which means 6. So that's the basic strategy. So of course, this performability theorem cannot you cannot hope it to be satisfied for general potential and for general these general shifts. So the condition that we need to assume is that the potential is bounded, uniformly continuous with a summable variation. So let me explain that what is meant by summable variation. So it means the following. So let's look at phi with two different inputs. But the inputs all agree in the first n symbols. In the first n symbols, the inputs all agree, and afterwards they can be anything. So let's take the supremum of this variation. So this difference, this supremum is called the var n of phi, the nth variation of the function phi, because the first n symbols are the same. And then I want these variations as a function of n to be summable. So that is why it is called the summable variation. So in our problem, because of the random walk in dimension d, you can compute, you can use the local limit theorem to bound the transition probabilities. So you can use it to show that in our case, our potential has a summable variation as long as the dimension is larger than or equal to 5. In particular, this allows you to put arbitrary initial condition from -infinity to 0 for the random walk. You can extend the random walk backwards in time in any way you want, and it has a negligible effect in the long run, thanks to the assumption that dimension is larger than or equal to 5. So that is essentially the key condition that you need to satisfy. So once you assume that, then indeed we can prove a version of the performability. So this, the proof of this result actually is, takes up most of the paper. Most of the paper was basically trying to prove this. So let me just recap what is the formulation statement of the perforability. So first they said that there is a positive eigenvalue, lambda, and there is also eigenfunction that is positive everywhere on the space of semi-infinite sequences, and there's a probability measure on the same space. So the function h is the eigenfunction with eigenvalue lambda. The measure nu, the probability measure nu, is the eigenmeasure of pi, the adjoint of pi, with the same eigenvalue lambda. And furthermore, if I look at the inner product or the integral of the function h against this eigenmeasure, then the integral is equal to 1. And lastly, the third condition is about convergence. Namely that if I apply this operator, transfer operator, to iterate it and apply it to in the test function for f, and normalize by the eigenvalue to the power of n, then this should converge to basically a multiple of the eigenfunction. So any initial function that you take, if I apply the operator pi repeatedly, then it will converge to the eigenfunction, where the constant multiple is simply the integral of the test function phi f against the eigenmeasure nu. So that is the convergence result that essentially entails some sort of mixing. A priori, this could be arbitrary weak form of mixing, and that is where we need the stronger assumptions to ensure quantitative fast mixing. But for the moment, we already have some sort of weak mixing. Okay, so when the alphabet is finite, this is a very classic result of Waters from 75. So our proof essentially follows the same strategy as Waters' paper. And subsequently, Sarik has studied the case when the alphabet is countable. And there have also been papers on the case when the alphabet is compact. When the alphabet is not compact, there have also been some papers. But in those papers, they require the potential phi to be so-called Holder continuous. So Holder continuous in that literature just means that the variation is has exponential decay. So remember that let me come back to it. So here's the variation. Summable just means that, so for example, if the variation decays like a polynomial with exponent strictly larger than 1, then it is already summable. And what they call Holder continuous potential means that the variation actually decays exponentially fast. So here we basically relax the assumption to the case where the potential just needs to be summable. So it does not need to have exponential decay. Okay, so that's a key result. And now let me explain briefly that once you have the Perron-Frobenius theorem, how do you do the H transform in case you're not familiar with this? So H transform just means that if you have an operator which has a positive eigenfunction and positive eigenvalue associated with it, then you can always change the kernel into a probability kernel in the following way. Namely that you have the transition here, and then you multiply by the eigenfunction, the positive eigenfunction H, and then you divide by the eigenfunction evaluated at your starting point. And then you normalize by the reciprocal of the eigenvalue. So if I take this as my new probability as my new kernel, and I integrate over the whole space, so let's replace A by the whole space, then you see that the numerator is exactly the action of the operator pi acting on the eigenfunction H. But since it's an eigenfunction, it will be exactly lambda times H of eta, the initial condition. So therefore it's 1. So therefore this defines a probability kernel. So that's what is meant by H transform. And furthermore, you can check that in our setting, this H transform Markov chain has a stationary probability distribution, has an invariant probability distribution, which is given exactly by the pairing of the eigenfunction and eigenmeasure. So you basically take the eigenmeasure nu, and then you multiply with the weight that is given by the eigenfunction. And so we already saw that in the Perron-Frobenius theorem, this has total mass 1, and so that's basically what we have here. So this measure here is a probability measure. It has total mass 1, and it's a invariant probability measure. Okay, so once you have that, then we are ready to basically reformulate our Gibbs measure on the symbols. The symbols are the increments of the random walk. So you take basically the normalized probability measure of the law of the increments, and now we are ready to rewrite everything in terms of the H transformed kernel to relate it to the stationary process for the H transformed Markov process. The important thing is that to relate to the stationary Markov process with kernel pi h, you need to distance yourself from the terminal time and the initial time. Because the initial time, there is a past history, so there's some boundary condition, which influences the distribution of the increments for a while. But if you place some gap between the increments you are interested in and the history, let's say anything that diverges will be sufficient, then the mixing will bring you into the stationary distribution. And similarly for the terminal time. For the terminal time, if you bring some gap to the terminal time, which also has a boundary effect, then again, you'll be close to the stationary distribution. So that is something that you have to do. So that's the lemma here. So once you do that, then basically we can just study the law of the increments on the stationary distribution of this H transformed Markov kernel pi h. And so this brings us to another second result that we need to adapt from the literature of thermodynamic formalism, namely that if I study the stationary process, nu h, so that will just be the probability measure on this infinite sequence of symbols, but it is translation invariant in the sense that if I cut away the first 100 coordinates, the distribution of the tail is still the same. It is translation invariant. So what we want to do is we want to deduce a mixing property for this. And so there is a classic result of Polycott, which was also for the case of a finite alphabet, where he showed that if the potential is a summable variation, then there is a quantitative mixing. And here we want to extend this result to the case where the alphabet is a Polish space equipped to the probability measure. Okay, so here is the result on the mixing. So let's assume that the variation of the potential phi decays like a power law with the exponent given by some number r. R is strictly larger than 1. And so the mixing will be formulated in terms of this the exponent of decay r here. So what is meant by mixing is the following. Suppose that I take a test function defined on the space of semi-infinite sequences. So what will be one particular example in our case? Well, in our case, we're interested in the displacement of the random walk, right? So this means that in every unit time interval, what I can do is I can simply look at the displacement of the random walk on that unit time interval. So this will be a vector analog of this test function here. And so we are interested in basically additive functionals of the sequence, which, for example, could simply be taken to be the summation of the increments on each of the unit intervals. So that will give basically approximation of the whole trajectory of the random walk. Now, mixing here means the following. So let's assume that the function f here depends only on the last symbol. If it depends on finitely many symbols, or if the dependence on the symbols in the history decays fast enough, that is also sufficient. But let's assume for simplicity that the function depends only on the last symbol. So in our case, it corresponds to the last increment of the random walk. Then you have a following bound on the L2 norm of the transfer operator pi h applied n times, iterated n times applied to the function f. So if you write it out, what is the meaning of this operation? It is simply the following. I condition on the entire history up to time minus n, and I look at what is the increment at time minus 1 to 0. So there is a gap between the increment I'm interested in and the history I'm conditioning on. So that, of course, decays with time. I look at the second moment of this. I look at the L2 norm of this random variable, and the assumption that L2 norm of this random variable decays polynomially, but at a slower rate. So here the potential decays like n to the power r. Here we have r minus 1, minus epsilon. So there is so that is the mixing result we need. And so now we are ready to apply a classic invariance principle of Pellegrad and Utev for mixing sequences, which says that for any mixing sequence, you can define a similar operator here. And so the result is that invariance principle holds if the exponent r here is strictly larger than 3/2. And in our case, this is true if dimension is strictly larger than 5. And so that's why the result is formulated for dimension larger than or equal to 6. Okay, so I think that's all I want to say. Thank you.
Thank you very much. Question?
So, what is the property of which helps you to prove the non-convenience theorem? Did you apply a compact correct?
Okay, so our technique is, so we try to follow the same strategy, but in Walters, they use basically fixed point arguments. You have an operator, and then on the space of probability measures on this sigma, and then you apply a fixed point argument. In our case, we cannot apply a fixed point argument, so what we do is that we truncate the space by compact sets. So on this compact set, you can define a sort of modified operator, which has a fixed point. But then you try to show that as you exhaust the compact set and make it larger and larger, exhaust the sigma, you have a sequence of fixed points. So they are all approximate fixed points of the fixed point that you want. And so we just show that this sequence of approximate fixed points must converge, and the limit must be a fixed point as well. And so that is the argument for the invariant measure. For the invariant function, for the eigenfunction, that requires a bit more work. And so there are some technical complications, which is why most of the paper is actually about proving this result.
Any other questions? Yeah?
So if I understood correctly, basically the invariance principle in dimension 3 in the mobile case is because you make a very small clearing, and then that clearing is moving around diffusively.
That's the heuristic. That's what we conjecture.
Right. And so I wonder, there is, so your environment, your Poisson cloud of walks that generate they have rate 1.
Yeah, they have a fixed rate. They have rate 1, yeah.
For instance, if you just take your first results where you had the Laplace transform or the survival probability, so if you make the mobile traps less mobile, make the rate smaller, do you recover the Danskov-Arden
Well, we have never looked at this, but yeah, we expect that there is interpolation, but the scale of interpolation may depend on time. So there will be a time-dependent scale interpolation which allows you to see how you transition from one to the other. Yeah, so it's not clear that, our techniques seem to break down at dimension 5, but the heuristic is suggested that maybe it's the same for all dimensions larger than equal to 3. But it's not clear that what techniques would allow you to prove such a result in dimension 3 and 4. 5, maybe you can work harder to still get past it, maybe.
But so intuitively, the thread, I mean, the clearing starts to become bigger and to move less, right? Somehow.
Yeah. You mean in the low dimensions? Yeah. Yeah.
Yeah, I mean, your d equals 6 thing seems to show up as some sort of technical
That's right.
outcome, but is there a way to just say, you know, that have some sort of absolute continuity thing, like, you know, when the thing has survived a long time, the environment is actually absolutely continuous with respect to the one? I mean, is there something of that sort that is underlying this?
We are not sure. We don't know. We haven't really looked at this because the mixing condition is sort of optimal, I think, for mixing sequence. That what condition on the decay do you need to get invariance principle? I think that is almost optimal. So this means that in dimension lower than 6, you're going to have basically mixing sequence which has a worse decay than the standard theorem for invariance principle. And do we still believe that for some special reason that because of the special structure of the problem, you still have an invariance principle? So that is not clear.
On your slide, I think it was the last one or last one, you refer to this central limit theorem for the, yes, there it is. So on the top line, you say that from invariance principle for macropolar with pH, for what kind of functions your invariance principle is? So you have some restrictions to the functions on what kind of functions f you could take.
Okay, so for f, it's very simple because we are interested in the position of the random walk. So we simply take the increment of the random walk. Let's say in the first coordinate. You take the first coordinate of the random walk increment from time 0 to 1. So that is a bounded random variable because we assume that underlying row random, no, sorry, that is not bounded, but you have a good control on it. And so in our case, f is basically the increment of the random walk on the unit time interval, which is a very well, nicely behaved random variable.
What is the condition? So you refer here to some theorem.
So that's this Pellegrin. The Pellegrin-Udev.
I see.
Yeah.
Okay.
So the condition is exactly on this operator. The pi n of pi n acting on the function f.
There is a theorem saying that if you have such a pi sub h, this kind of Fermat-Frobenius type of thing, then once this mixing exponent r is greater than 3/2, you have a central limit theorem.
Yeah. So for Pellegrin-Udev, you basically have a stationary process, and then the condition is exactly on this operator.
So that's not related to.
So this is not related to thermodynamic formalism.
Yeah. Okay.
And so once this is true, then you have an invariance principle.
Offer.
Would things be easier if the random walk was in discrete time?
Yeah, if it is in discrete time, we can just use results from the literature.
Right?
We can just quote the Perron-Frobenius theorem from
Exactly.
the.
Either in that situation, do you still have a restriction on dimension? What is the
It's
restriction
the same.
on
It's the same.
dimension?
It's the same.
It's the same.
Yeah. So our results for this sort of non-compact alphabet space is matches with results for the discrete setting.
What are the results for the discrete case?
Something like Polycot's result is basically the same as same result here. That's this is Polycot's result.
I understand, but these were not known. I mean, the one for Venus, yes, was known before, but the results on the walk was
So that was not known. So that was not known. I mean, it's just that the previous paper.
Hard work is just to get from discrete.
Yeah, I mean, the reason why we do this is because all the previous papers we consider continuous time, and so we don't suddenly want to switch to discrete time. So we work super hard to prove the Perron-Frobenius theorem.
But to do that, can't you approach it by taking the discrete walk? In short time increments.
Okay, so what you can
this way.
Yeah, what you can do is that you can do a different way of decomposition in time. You wait for stopping time. Like the first time random walk makes a jump, and then you cut it,
You
and
can
then
do that also.
Yeah, you can do that. Yeah, and we didn't try to do that because we already sort of quite far through so this proof. So.
Okay, I rest my case.
It's time for lunch, so let's thank Rongfeng again.